Okay, well, hello, good morning, everybody. Thank you very much for coming to my talk about low latency C++. We have 3 hours and 400 slides, so strap in. It's going to be a good ride. Just very quickly who I am. My name is Timur Doumler. I work at JetBrains. I'm a developer advocate. We make developer products such as C-Line, which is our C++ IDE, ReSharper C++, which is an extension for Visual Studio, and Rider, which is our IDE for .NET and Unreal Engine development. I'm also hosting CppCast, which some of you might know. But the thing that actually kind of brings me here today with this talk is that I've also spent about a decade working in the music tech industry, in particular music production software. And I'm kind of still a bit involved in that. I co-founded a company 4 years ago called Cradle. We make music production software. This is the Spirit. This is our latest one. It's like a vocal processor. This is the kind of stuff that you use if you produce music that you hear on the radio or a soundtrack for a Hollywood movie or something like this. And so audio is one of those industries where we use low latency and real-time programming because it's kind of a real-time problem. And so that brought me to give quite a few talks over the last 8 years or so about low latency and real-time programming. And some of those talks do have audio in the title, but the vast majority of the content isn't really very specific to audio. And this is actually something I discovered as I started giving these talks, that actually a lot of the techniques that we use are kind of very similar to the techniques that other industries use that are in this low latency and real-time kind of field, let's say. So notably, video games are in this space, and certain financial use cases like high-frequency trading, low-latency trading, this kind of stuff. And then a lot of embedded development like automotive, aeronautics, robotics, medical, etc., etc. Those industries also write code where low latency is important, and sometimes you have real-time constraints that you need to satisfy. And as I started giving talks about the stuff, I found out like a few interesting things. One of them was that a lot of the solutions that we use in audio are actually also to an extent applicable to these other industries. So I had feedback from people who are not in audio but in some of these other industries approaching me and saying, hey, this is useful, this is relevant, this is kind of similar to what you're doing. You're solving similar problems. But also, like, the reverse was also true. Like, when I was looking for solutions in the audio space, I started looking for what the gaming people are doing or what the high-frequency trading people are doing, and going to their talks, and reading their blog posts. And it turns out that quite a few times I found a solution there that was perfectly applicable to the stuff that I was doing in audio, but the people I was working with in the audio industry didn't know about that, right? So I found that this kind of exchange across industries was really productive, and I learned a lot from that, and conferences like this one I think are a great place for this kind of stuff. And so really what brought me here today is that I kind of wanted to look back at all of these talks that I've given and of other stuff that I've learned in this space and do kind of like a high-level overview of all of the stuff. Okay, so I got a double slot for this. Thank you very much, CppNow. So what I'm going to do different from my other talks is that I'm not going to go super deep into any of the particular solutions. It is going to be more like a high-level overview. So if you are already a low-latency expert, chances are you're probably not going to learn much new stuff. So apologies for that. And the other thing that I'm really interested in is getting your feedback about this material. Like, if you feel like, especially if you work in any of the other industries, like not audio, but like video games or trading or embedded, I would love to hear from you, hey, this is very similar to what you're doing, or no, you're doing this other thing, or this is completely not relevant for me, or something like that, right? So this is the kind of feedback that I would be really interested in, because what I kind of find really fascinating about this field, after having given these talks and after having learned all the stuff from the other people, is that there is this common thread. There's a common feel to what low latency and real-time programming actually is and how you do things there that kind of transcends these industries. And I'm kind of not sure yet to what extent that's true, because obviously you do have different constraints, different use cases, et cetera, et cetera. So I'm really interested in hearing feedback about this, right? Because obviously I am a little bit biased coming from audio and not having worked in any of these other industries. So speaking of which, This talk is not going to be about embedded because I've never worked in embedded. So I think a lot of the stuff, especially in the second part of the talk, where we talk about you can't allocate and things like that, I think are very similar in embedded. But also embedded systems have their own constraints, right? You're not on like a laptop like this. You're on a very constrained device. Maybe you have a real-time operating system or bare metal, no operating system at all. You're very constrained in terms of memory or what your processor can do. And those additional things, like I don't really have any experience with those, so I'm not going to be covering the specifics of those kind of embedded systems. I also don't really know much about other architectures like mainframes or exotic architectures. Like all I've ever done really is, x86 and ARM, and then Windows, Mac, Linux, iOS, Android. So I don't really know anything about anything else, but I'm interested in hearing like what's different, there. I also don't know much about GPUs, so I'm not going to talk about that at all, or other forms of heterogeneous computing. And the other things I'm not going to talk about is safety and security, surprisingly, for this conference. This is a talk that is not going to go into that topic. I'm also not going to talk about language design, and I'm also definitely not going to talk about C++ successor languages. So I'm sorry if this is what you're primarily interested in. You should go to one of the other talks. What we're going to talk about is low latency. So what actually is low latency? And what does that have to do with this other buzzword, performance, right? So it turns out that one way you can look at this is you can say that performance is actually these like two orthogonal components, right? There's latency and there's throughput. And if you visualize your program as like a pipe and there's like information flowing through, then the throughput is how much data you can process per unit of time. And latency is how much time is going to pass between you asking the program a question and the program giving you an answer, right? And so those are kind of orthogonal aspects of performance. And interestingly, you might want to optimize for one or the other, or some kind of compromise of both, depending on what you're actually doing, what your use case is, right? So it seems like there seems to be some kind of spectrum. And on the very left, there's going to be use cases where you really want to optimize for low latency. You don't really care that much about throughput or bandwidth, which I'm going to use as synonyms. And then on the right, there's use cases where you really, really care about bandwidth and throughput, and latency isn't too much of a concern. And depending on where you are on the spectrum, you're going to choose different techniques and choose different trade-offs and use different tools and use C++ in a different way. And so, as a first approximation, we can say that, if you work at, Google or Facebook or any of these companies, you have a huge server processing, millions of requests, then you're probably somewhere in the middle. You obviously do care about latency because you do care about, the server giving you a response within a reasonable amount of time. But you also really care about bandwidth because you have probably hundreds of threads going on, thousands of requests going on. And so you want to be in this kind of sweet spot, right, where like latency and throughput are kind of like utilizing what you have optimally to like get both. And so this is exactly not what I'm going to be talking about, right? And so on the other end on the far right end of the spectrum is the stuff that I'm also not going to talk about, which I've actually started my coding career in there, kind of scientific simulations, and like some people call this high performance computing. Or high-performance computing probably means something else. It's a broader umbrella. Like, let's not go into that rabbit hole. But like stuff like scientific simulations, where you really, really care about throughput, right? You're processing gigabytes of data. You run some kind of simulation. You really want it to be fast, right? You care a lot about your simulation taking 5 days and not 10 days, right? Because that's like a lot of money, a lot of CPU time, et cetera, et cetera. So you really care about performance, but you don't care about latency. You don't care about how much an individual time step within that simulation takes, and if it takes longer than whatever. You don't really care about that, right? You care about processing all of this data and getting a result at the very end, and that being as efficient as possible. So that's not, again, not the stuff that I'm going to be talking about. What I'm going to be talking about is everything that's kind of to the left of the middle here. And I think we can also distinguish a little bit. So in video games, I would say you also care about both low latency and also bandwidth, because you're going to be rendering lots of monsters on the screen. That's a lot of data. So you do care about bandwidth, but you're kind of a little bit more to the left, because if you have a choice, you're probably going to choose latency over throughput, right? So if like you're starting to drop frames, what you're going to do is you're not going to reduce the frame rate. What you're going to do is you're going to reduce the amount of stuff that you're going to be rendering. You're going to be reducing the throughput because you don't want to have dropped frames. So you are a little bit to the left, of that spectrum. And then, with the other use cases, if you talk about real-time audio processing or especially high-frequency trading, low latency is really pretty much your only concern. That's where all the business value of your products comes from, and everything else is kind of secondary. Right? So you're like then on the very far end of the spectrum. And depending on what you're doing, you're going to be optimizing differently and choosing different things. One way I can visualize this, forgive me for the poor quality of this drawing, is you have a intersection in a road, and these are supposed to be traffic lights, and you want to kind of improve the traffic flow across this junction, right? And so if you're optimizing for high throughput, you're going to add more lanes, right? And then you're going to have more cars that can go through this junction per unit of time. If you're somewhere in between, you're running a server, for example, this kind of stuff, you're probably going to be optimizing for some kind of compromise for both. And so one thing that's, I don't think very common here in the US, but very common in Europe, you have these roundabouts where you don't actually have to wait at the red traffic light. So that kind of helps both latency and throughput as well. So these are kind of the solutions you end up with if you're dealing with that. If you're optimizing for low latency, typically the scenario is different. And you have certain types of cars, like buses, for example, and you want the buses to not stop at the red traffic light or not be stuck in traffic. And you don't care so much about the other cars. So one thing that you might be introducing is you might be introducing a bus lane, right? Which again, in Europe, we have lots of those, where only the bus can use the bus lane. And then that's not going to do anything about the throughput of the buses, because you're still going to have one bus coming every 10 minutes, but the bus is not going to be stuck in traffic. So you're going to improve the latency of that bus arriving somewhere. And if you really care about latency, what you're actually going to be doing is you're going to get rid of this whole intersection. And you're going to say, okay, this bus should just not stop. And it should just not be, the latency should not be compromised by any other aspects of my system. So you're actually not going to have a junction at all. You're just going to have a bus lane, and then the cars go under it or around it or something like this, right? And so this is really what I mean by kind of low latency programming. And I guess another analogy is I don't know, you have a marathon going on, and then, or some kind of race in your city, and you don't want any of these people to stop at a red traffic light, right? So what you're going to be doing is you're going to be routing the whole traffic of the whole city around those people, so that they're not going to get in the way. And for the total efficiency of traffic in the city, it's going to be horrible, right? It's going to be, most people are going to be late for work if they don't know that this is going on. But the runners are going to arrive where they have to be as fast as possible. And so this is really what low latency is about. This is what you want to do. And it seems like there's always this notion of a hot path, right? There's always some aspect of your system where that's the thing where you want the latency to be really, really low. And so what you can look at is what's the topology of this hot path. And it's kind of interesting, again, that across industries there are some similarities. So in audio, typically what we have is we have one audio thread, which is doing the audio processing, and then the sound card gives you a callback every 1 to 10 milliseconds, depending on your buffer size and sample rate and all of that stuff. And then you have this time to fill in the buffer before the next callback comes. And then if you're too late, then you're going to get a buffer with garbage. You're going to have a glitch, which is not good, right? So you have these regular callbacks, and then you have a limited amount of time to produce the output. And then you have other threads rendering the GUI or processing MIDI messages if you're playing a keyboard or reading files on network or whatever. And they don't have these real-time constraints, and you somehow need to synchronize them. But the hot path is kind of, it's kind of dependent on this callback, which is ultimately a quartz crystal somewhere in the sound card that's giving you this regular pulse. And it seems like in many embedded applications, actually it's very, very similar. You might not get a callback from the operating system. You might get an interrupt, right? But it might be similar. You get an interrupt. Oh, there is new sensor data. You need to move the robot arm now, and then you have a very limited amount of time to produce that data. So in some applications, it might not be a regular callback. It might be like kind of irregular. You might not always have to produce output. Like I think in high frequency trading, I'm actually not sure if that callback is regular or irregular. Maybe somebody can tell me. But you don't always like send an order or do something. I think most of the time you don't actually do anything. But kind of there is a similar topology going on, that there's something happening and then you have to react as fast as possible. Gaming is kind of the weird one in a way that in a lot of kind of consoles or like PC games, you actually do the hot path on multiple threads. Like all the other stuff, you have like one hot path is typically one thread. That's like another big difference from like these big servers where they optimize for kind of performance in general. In gaming, you often have multiple threads rendering, but you also have this deadline, right? You have like, something like 16 milliseconds if you're rendering on 60 hertz to render the frame, and if you don't do that in time, you're going to drop a frame, which is not good. So it's kind of similar to the audio thing, but like just on multiple threads. And then another thing that some embedded systems have is that they have this super loop where you don't have threads at all. You just have one infinite loop in the main, and then it's just doing the things that it needs to do, like in order, like the sensor, this sensor, this sensor, and then it goes round again, round again, round again. So it's a little bit different. You don't have this regular callback, but you do have the same problem that if one of these tasks takes too long, it's blocking all the other tasks. You don't want that. You want to be as fast as possible. So we have these slightly different topologies, but we have this common notion of a hot path. Right, where like it really matters that this bit of your program, which often but not always is one thread, is as fast as possible. And so that's low latency. What's real time? Real time is kind of a little bit on top of that, is when not only does it have to be as fast as possible, but there's actually a deadline. And if it's slower than that, then that's not acceptable, basically. So to the first approximation, one definition of real-time is that in order to be considered correct, not only does the program have to produce the correct result, but it also has to produce it within a certain amount of time. And if the result comes too late, it's considered incorrect, even if it's numerically or whatever the correct result. So that's the big difference between like real-time programming and normal programming, right? Normally, if you write C++, you don't have these constraints. For these use cases, we do. And so one thing that's interesting is that a lot of these use cases have this thing in common, that they have a deadline, but it's vastly different how long that is. So if you're writing a video game and you're rendering frames, you're talking about something like 10 milliseconds, 16 milliseconds if you're rendering at 60 hertz. If you're doing audio processing, you're somewhere between 1 and 10 milliseconds to render an audio buffer, probably on the lower side of that, like 2-3 milliseconds. That's kind of very typical. If you're doing high-frequency trading, you're way more to the left, right? So if you're doing something in C++, you probably want to have a latency of something around a microsecond to place the order. And if you're doing like FPGA stuff, then you're in nanosecond territory, right? So there's like all these orders of magnitude in between. And embedded I drew as this like long thing because it really depends on the use case. Embedded is such a vast field, right? Like it really depends on the use case what your deadline is. But that is not a huge amount of time, right? So if you take this kind of 1 microsecond, that is the time that it takes light to travel 300 meters, right? Which is the height of the Eiffel Tower. So that's not really a long time at all. And so, you kind of care about latency in other use cases as well. If you just have like a completely normal app and you have some buttons going on there, you also don't want the latency to be more than something like 100 milliseconds, which is kind of the threshold at which people start to notice that it's a bit laggy, right? But I think the difference here is that reaching that kind of latency isn't that hard that it becomes like the dominant problem that you need to solve. Like if you use a GUI framework, typically if you don't mess up really badly, you kind of just get that out of the box. So that's not going to be your primary concern. And so I'm going to draw another line here and say kind of the stuff to the left is kind of what I call low latency programming, and the other stuff probably isn't. And so another thing that's important is what happens if you miss your deadline. Oh, I should say also, Another interesting difference, I think, between trading and the rest, and please, trading people, correct me if I'm wrong, is that with all the others, you know your deadline. Like with gaming or audio processing, you know exactly how many milliseconds or microseconds you have before you run into trouble. With this kind of high-frequency trading, I think it's more like you have to be faster than everybody else to get the order through, right? But you don't know how fast everybody else is. So you kind of probably have like an order of magnitude kind of understanding of it, but it's not that the deadline is given by your system, right? It's kind of something that you just have to be as fast as possible, and faster than, not as fast as possible, you have to be faster than everybody else. So there is a deadline, but you don't know exactly how long that is. So I think that's another curious peculiarity here, which it's going to pop up later, I think, in a few places as well. So what are the consequences of missing the deadline? And it seems like it vastly depends, right? In gaming, you drop a video frame. If it happens very occasionally, probably nobody's going to notice. No, maybe somebody will notice, but it's not that if you drop one frame, your game is completely useless, right? With audio, it's more, and please, gaming people, like that's true for everything I'm saying. I'm talking about industries where I don't actually work in. So if I'm saying something that isn't right, please find me and correct me, because I'm really interested in that kind of feedback. Yes?
So gaming also really depends on the platform, right? So on PC, you can have a sort of variable frame rate, but on a console, if you're fixed to like an NTSC, you drop a frame, you're halving the frame rate. You go from 60 to 30.
Yes. So the comment was that you can have a flexible frame rate, for example, on a PC game, whereas on a console it's fixed. So it's a lot more kind of deterministic, that you know how much time you have.
When you drop, you halve the frame rate.
So when you drop on a console, you actually halve the frame rate. You don't have this like sliding scale of frame rate going on. Okay, that's interesting. It's another comment.
So I just want to comment, not entirely true. So now the new consoles have the various refreshing rates. So
okay.
Now it's like
now that we have
so it depends. It depends on the hardware. Like the comment was that some consoles actually do have this variable frame rate. So I guess it depends on the hardware.
on TVs.
I think in gaming and audio, as far as I understand, if you're much better, much faster than the deadline, then the user, the customer won't.
You're gonna get to that.
Okay.
So in audio, like it's actually a lot worse, because even a single dropped audio frame, you really hear it. Like it's like this audible like pop or glitch or click. And so, you know, if you're listening to a podcast on your phone, you probably don't care. But if you're using like something like the stuff that we do at Cradle, right? Like if you have like a vocal processor and somebody's producing the next hit, and then, you know, they apply this effect, and then there's like a glitch in there. Like you're gonna throw that piece of software out and never gonna use it again.
Can I ask why there's an audible glitch? Why does it not just go quiet?
Because like, comment, why is there a glitch? Like listen to my other like audio talks, but basically the audio signal is continuous, and if you drop like one frame or one buffer, you have a discontinuity in there, and then the human ear is very sensitive to discontinuities in an audio signal. Like it's not. Let's talk about this later. It's an interesting topic, but it has nothing to do with this talk. But yeah, dropping a frame is really bad in audio. In trading, I think it's even worse, because not only is your product useless that you're selling, but you're not actually selling it to end customers. You're kind of running it yourself, and you want to make money, and you can lose a lot of money if you're not fast enough. And so in embedded, it's even worse than that. You know, in some use cases like medical or aeronautics or something like this, you know, potentially if you fail to meet your deadline, there can be human lives on the line. This is kind of the stuff that we were talking about in the safety discussion yesterday. So this brings us to these kind of definitions of hard real-time, firm real-time, and soft real-time, which some people use, where hard real-time is the kind of stuff where somebody might die. Like any missed deadline is a complete failure of the system, and you must not have that. And that's kind of the stuff where you start having things like a real-time operating system with a deterministic threat scheduler that ensures that, you know, certain time constraints are going to be upheld and stuff like that. Then we have firm real-time, where, you know, if you miss a deadline, it might not be a complete system failure, but like whatever result you get back after the deadline is useless, right? So this is maybe the case in certain, if you're listening to a piece of music on your phone, you're dropping a frame, you have this glitch, you're probably not going to throw out the whole thing, but your app produced a result that's never going to end up being output through the speakers, right? It's worthless. And then there's soft real time where you can tolerate missed deadlines, and it's sometimes fine not to hit the deadline, but the value of a result produced after the deadline kind of goes down over time. Right? And so one last definition here is jitter. And it kind of, I think, can refer to two different things. If you have this scenario where you have like a regular callback, like an audio or a regular interrupt or something like this, jitter can both refer to how regular these interrupts are. And it's not good if they're not as regular. Like, for example, in audio, different operating systems like have different amounts of stability in terms of like how precisely timed this callback is. Kind of depends on the audio stack of the operating system. But then jitter can also mean how long does it take for you to produce the result. And in some use cases, it's not a good thing if that takes a certain amount of time sometimes and a different amount of time other times. And if you're kind of on the left-hand side of the spectrum, it kind of really depends on the use case, really. And so this, I think, is something that we were alluded to earlier a little bit. Which one would you choose here, right? If you have, if you're producing a result, regularly on some kind of callback, and then it's going to go and do something, and then it takes 1 microsecond almost all of the time, but every once in a while, it takes 5 times or 10 times longer. Is that better, or is it better if, like, you kind of have a deterministic upper bound, and you can say it's never going to take more than 1.8 microseconds, but it's gonna be kind of more longer on average, right? So you're going to consume more resources on average to get the result. So, a quick show of hands: who prefers the left one?
I think it depends on what you're trying to do.
Yeah. So it really completely depends on what you're trying to do, and even within the low latency space. Like in audio, or if you're rendering like frames in video frames, audio frames, whatever, you're definitely on the right-hand side there. Like you do want the right-hand side always. I think in kind of safety-critical applications that are also low latency and real-time, you're also, I think, pretty firmly on the right-hand side. And I think if you're doing high-frequency trading, please correct me if I'm wrong, people, I think at least in some of these use cases, you are kind of on the left because you don't care about every trade going through. You care about some trades going through, and for those, you want them to be faster than everybody else and as fast as possible. So you're kind of more on the left-hand side of this. So you can actually say that it's not really a spectrum. We can kind of bifurcate it and say, okay, if you're kind of more on the left side, then you're doing kind of ultra-low latency. You care about the latency being as low as possible. But if you're on the right-hand side, you're probably doing real-time programming where you care more about reasoning deterministically about not ever being slower than a certain amount. And so like you're optimizing for the worst case, right? And so one last term here I think that's important is efficiency. And you hear a lot about efficient programming. And I think somebody in the audience wrote a book called Writing Efficient Programs. Don't know if Fedor is still around. I think he is. I'm blinded by the light, so I don't see if he's in the room. But so efficient programming is a big topic. My definition of this, and it's maybe a bit vague, and oh, there it is. I see you now, Fedor.
Oh,
okay.
Me?
Yes. One way I would define efficiency is like this. I would say that, well, to program efficiently is to reduce the amount of work that the program, or maybe the amount of energy that the program has to spend, or the amount of work that the program has to do to perform a certain task. Okay, and so it seems like if you're on the spectrum, efficiency is right in the middle, and it really benefits both, right? So, for example, another traffic analogy: if you're optimizing for high throughput, you want to be maybe adding more lanes. If you're optimizing for low latency, you might invent something like the telegraph, right? Where like the bandwidth goes down massively. Like in the telegram, you can put a lot less information than in a big letter or something like this. But you can transmit it a lot faster than the letter, by horse or by car or whatever, right? So this is really optimizing for low latency, but efficiency is right in between. Efficiency is like inventing the wheel, right? Where that lets you get the stuff both faster from A to B, but also lets you transport more stuff. Right? So if you do efficient programming, you get both better throughput and better latency. And so what we're going to do is we're going to look at efficiency in the remainder of the first part. Then we're going to look at the kind of the low latency stuff, the more specific latency stuff in the second part. So one last thing before I start talking about more code kind of stuff is that one thing I found interesting is that also like what hardware do these low latency and real-time use cases run on? And there's like a vast difference, right? So if you're on an embedded system, you can have this like tiny microchip, and you might have a real-time operating system there, or you know, so you're gonna be working on a very constrained system, but you're probably gonna have a very high amount of control over that system. You're probably gonna be designing the PCB yourself, or maybe you take something off the shelf, but you have a high degree of control over exactly what hardware you're running on. If you're doing games or audio, you know, these are some, you know, things that I was involved in previous steps of my career. You sometimes also have, you know, embedded devices like a keyboard or something, but like a lot of the stuff also just runs on consumer phones and consumer laptops, and then you just don't really have any control, you know, over that. Like somebody can have the latest phone, or like a crappy phone from 10 years ago, or like a really powerful gaming laptop, or like a really crappy laptop, and your software kind of has to run on all of these things, and you don't really control what's going on, like what resources you have. And I think maybe not so much in gaming, but in audio, you kind of also do cross-platform development, right? So you want to ship on Windows and Mac and probably Linux and probably phones and on all of those, right? So you have even less control over, kind of, you can reason even less about what kind of system you're going to be running on. Then we have gaming, which, you know, you can have on PCs, but you can also have on consoles. I think on consoles you have a pretty precise specification, so sometimes you do know. And then if you do kind of this kind of high frequency trading stuff, I think you're kind of designing your server exactly with your requirements in mind, right? You buy this exact server and you have this like solar flare network card in there, which has like these specifications and give you this latency, and you put them all in there and in some kind of you know, server facility or whatever, and you have a high. So it seems like it's a very different, both how many resources you have, and can range from very little to a lot, and how much control you have over what system you're running on, what hardware you're running on. And again, it can range from very little to a lot. And so it seems like there is this kind of variation in all of these industries. But what they all have in common is that there's always this notion of a hot path, and there's always this notion of a deadline, right? And so that makes them different from a lot of other programs that people write. And another thing that they have in common is that C++ is still the dominating programming language, right? And so why is that? Well, of course, we have manual memory management, right? No garbage collector, no stuff that can slow us down. We can reason about that kind of stuff. It makes it a lot easier to like reason about how fast something is. Well, C has that too, but what C doesn't have is scalable zero-cost abstractions, right? Templates, algorithms, that kind of stuff. I mean, Rust has that too, but the thing that Rust doesn't have is the huge body of existing libraries and frameworks that C++ has, right? So if you're doing audio, like Juice is a framework that I think about 80% of every audio plugin is written in. If you're doing gaming, there's things like the Unreal Engine, right? I don't think there exists anything like this in the language like Rust, right? So that's why we're kind of here and we're doing C++. And but how are you writing C++? And it turns out that if you work in any of these industries, you write C++ in a different way, right? If you're on the left-hand side of the spectrum. And so I would say there's like kind of two categories. There's like something that I call efficient programming, and there's something which is kind of this hard real-time stuff where you program for deterministic execution time and you optimize for the worst case. So they lead to kind of, there's like two different categories of programming. But before we get into those, like obviously the most crucial thing is to measure. And so with all of the stuff, if you care about performance, you care about latency in particular, you don't know whether your latency is good until you actually measure it, right? And so one thing that I see again and again and again is that the results are often not at all what you think. Yes.
Regarding your previous slide,
Yes.
I think efficiency goes both ways. When you need latency, you need your handlers to be very efficient.
Yes.
It's rather throughput versus latency.
Yes, that's what I said, that efficiency is kind of in between, right? Efficiency benefits you if you both for throughput and for latency, right? So coming back to measuring, a lot of the time you get very surprising results. So I read Fyodor's book, The Art of Writing Efficient Programs. I enjoyed it. He has like a very interesting example there where there's a piece of code and then you transform it so it does less, but then it's actually slower. And that doesn't make sense unless you know a lot about what's going on. Another example that I really liked, like I encourage you to go to CPP on C, which is a conference in the UK in June where Dave Rowland, who's a friend of mine from the audio industry, is going to talk about optimization. And it's not an audio specific talk at all, it's more about optimization. He has an example there which is really interesting where he measured that min-max in a standard library is actually slower than just min or just, faster than just min or just max. And it's completely counterintuitive. And then kind of he dives in and figures out why that is, and it's quite interesting. And there's like another C++ weekly episode from Jason Turner that I watched like a couple days ago where like there was also some very surprising benchmarking going on there. So yeah, always measure, and if you don't measure then you don't really care about your performance, right? So we have a lot of tools to do this, right? So we have profiling. That's a good tool that we have. We have lots of tools for that. There's this kind of difference between sampling profiling and instrumentation profiling. Mathieu Robert had a very good talk, a kind of introduction talk to profiling about this at CppCon 2021, where he talks about that difference and like other aspects of profiling. There's also Chandler Caruth's talk from a few more years back, which is a lot more kind of low level, hands-on, but I also found very interesting. There's other types of performance analysis you can do, right? There's tools like perfstat or cache grind, which lets you measure cache misses. There's other tools that lets you measure, I think perfstat does that as well, actually. You can measure branch mispredict, syscalls, allocations, all of that kind of stuff. You can measure the performance of individual machine instructions on a particular CPU, right? You can look at the assembly that your compiler has generated for you. A common trap is that something that I thought for a long time before I started measuring is that a lot of the time you're kind of tricked into this thinking that if you have fewer instructions, it's going to run faster, and it turns out that's often actually not the case. And so, yeah, we have obviously Compiler Explorer for that, which everybody loves. And I have to plug our product. In one slide, I have to do that. I mean, I don't have to do that, but I want to because it's awesome. We introduced in C-Line another feature called Disassembly on Demand, where you can not just look at the assembly the way you can look in Compiler Explorer, but you can actually debug. And you have like code and disassembly kind of in parallel. You have both at the same time. You step through both at the same time. It shows you exactly like what line of code corresponds to what instruction. You can set breakpoints in both and jump around, and it's really, really cool for that kind of stuff. And then we also have just benchmarking, right? Measuring how long something takes, and I think that's really the most important thing here. We have various benchmarking frameworks. We also have QuickBench, which is kind of this online thing, which is really cool. And then obviously there's these two different ways you can benchmark your code. You can benchmark your actual code, which is what you ideally should be doing. But if you want to find something out about a very particular part of your algorithm and how fast that is, you can do micro benchmarks, which are very tricky, right? So a lot of the time, if you do micro benchmarks, you're not actually measuring at all how your code would perform in a real program, because you might have cache misses in a micro benchmark because your cache is not warm the way it would be in the real application. So you got to warm the cache. Your allocations are going to be different, right? If you benchmark std vector versus std list, right, and you allocate a std list with 1,000 elements just in your micro benchmark, they're going to be all consecutive. So it's going to be slower than vector, but because it kind of consumes more memory, it's not quite but it's going to be like traversing the list is going to be pretty much kind of contiguous traversal, whereas in your real program, if you remove and add nodes in the list, they might be all over the place, right? You might have a very fragmented heap, which will have very, very different performance characteristics. And then I think the biggest problem I see with micro benchmarks is that you kind of have to compile them the same way you compile the actual program, right? With the same flags. Like, it doesn't really give you anything if you measure, in debug, but then you ship release. But the problem is that if you turn on all the optimizations the way you do in production, but you have a micro benchmark, a lot of stuff is going to get optimized away in a way that isn't going to be optimized away in your real program. So you're going to be measuring something entirely different, right? So for example, if you have input data and the compiler can see it because it's right there and it's not in a file or in a translation unit, it can just const export away everything, right? A lot of the time. Or, if it can look into a function definition and optimize, inline it, optimize out a lot of stuff. And in the real program, maybe it's in a different translation unit, right? So you're going to often get completely different performance characteristics than the thing that you actually want to measure if you're not very, very careful about setting up your micro benchmark. Right. So the most crucial thing is measuring. And then, the other thing that we need to do is we need to write code. And for that, I think there are these techniques that I really want to separate into these two different categories. So one category is programming efficiently, which means you do the same thing but with less work or less energy, and that is very good for low latency. It's also very good for high throughput, right? So that is something that we can talk about, which benefits, I would say, most use cases of C++, or maybe all of them. And this is maybe something that everybody should be doing. And the only difference with low latency there is maybe that you maybe focus on some aspects of this a lot more. You have this hyper focus on performance, so you might take it a bit further with the efficiency tricks than other people. And there's a trade-off between something that runs fast and something that is clean code, for example, and you might have a different trade-off there. And then there is the kind of second bucket, which is you want to program not just efficiently, but you want to program in a way that you can reason about how long your code takes to execute, and that it can never execute longer than a certain threshold. Right? And so what I want to do is I want to talk about the first bucket in the remainder of this half. And then the entire second half of the talk is going to be about the second bucket, how you program if you have if you have a hard deadline, and you need to program for deterministic execution time. And there you find techniques that are going to be very different from what other people are doing, right? And I would say efficient programming is a lot more widely applicable. So if writing efficient code is such a huge topic, right? Countless blog posts and talks about this. So I'm going to just scratch the surface and mention a few talks and techniques here and there, but probably you're not going to learn much new here if you've been doing this for a while. So my goal is to just give a little bit of a systematic overview. So if you want to write efficient code, you obviously have to know the programming language really well, the libraries you use, and you have to know your compiler really well. The optimizer can do really weird, interesting things depending on what compiler you use, which can have a lot of impact on your performance. You got to know your ABI, right? Things like if you have a non-trivial destructor, then on Itanium ABI, it's not going to be put in a register. It might, have measurable effects on performance, stuff like that. And then you have to really know the hardware that you're running on, with the problem that in some cases you don't actually know the hardware you're running on. So you need to keep in mind kind of the general aspect of hardware. And then in other cases, you need to program for exact hardware that you're using, right? So the first kind of half of this, that's the stuff where I think there is a lot of material out there. There's all of these blog posts and talks and books about efficient programming. So I think this is kind of relatively easy to gain kind of experience with, whereas I think the second half is kind of a bit more difficult. I think the resources are kind of more scarce. But yeah, okay, so writing efficient code, let's talk about the hardware-specific stuff a bit later. You need to know the language, right? So one thing that comes up a lot is just avoiding unnecessary work. This is really at the core of all of this, right? So something that comes up surprisingly often is avoid unnecessary copies, avoid unnecessary creation of objects, right? So here's one example. It doesn't really matter what this does too much. We have a vector of strings, right? We have a kind of prefix string, and then we capture that by reference in this lambda, and then we do something to all the elements in the vector. We kind of append prefix plus another string. And so obviously the problem here is that we're creating a new string every time in the loop, because it is actually going to be a loop. So we're going to create lots of temporary string objects, even though the result is always the same. And optimizers are supposed to optimize this away for us a lot of the time, but sometimes they can't. So we need to do it manually. And then one thing we can do is we can know about the fact that lambdas have init captures and move that into the init capture, and then you just do it once, right? So this is kind of a very easy transformation that sometimes the optimizer can't do for us. This isn't really very specific to C++, I would say, and here now you just do this, right? This isn't very specific to C++, and those are the kind of cases you're going to see probably in all programming language. You have these things that you can do, and you can just have to see them. But a lot of the stuff is actually specific. You kind of have to know the language, right? So this is a classic that I see everywhere, right? Is that you iterate over a container, and then you take the stuff by value, and then you create all of these copies. And it can be I have seen this in production, that somebody removed this, and it was in the hot path of like audio processing, and then like that sped up everything by like 10x, just doing this instead, right? And so if you know how references work, you're fine, but no, a lot of people don't. And sometimes you also need to know the library that you're working in. For example, the standard library. This is another example here where somebody's iterating over a map, and then they actually do not use auto. Sometimes there are reasons why you don't want to do that, and they wrote like what they thought was the element type of map, but of course that's not the element type of map. The element type of map is still a pair constant widget. And so if you don't know that, you get an implicit conversion there, and you create another object there, and it's going to give you a massive slowdown. If you have a good IDE, obviously, like it's going to hopefully warn you about this kind of stuff. So CppTidy does have a warning about this specific case now, which is good. But there are a lot of cases where CppTidy or your IDE or other tool that you're using does not have a warning for it, right? So you have to know the language, you have to know the library. Other types of unnecessary work, apart from creating objects, is function calls, indirections, right? So there are many examples in these like efficient coding blog posts and talks where inlining a function makes a huge difference. Sometimes the compiler cannot do that by themselves. Then there is like this platform-specific force inline thing, which can give you a lot of performance, but you can also overuse it, right? If you put it on everything, you get code bloat. It's not good for the instruction cache and other things. So it can also slow down your program, right? So you have to measure. Like it can either be a slowdown or a speed up, depending on what you're doing. Virtual functions is another thing. Like if you have a virtual function, you get probably at least 2 instruction cache misses, right? One for the indirection, and then you have the indirection and then vtable. In the vtable, you jump to the actual function, right? So often that is a measurable slowdown. So you can use the variant, you can use compile time polymorphism, right? CRTP, deducing this, which is the feature we have in CppCast, which makes CRTP a lot easier. And then something that also has so many talks about this, and they're great. Make as many decisions as possible at compile time. Const export all the things, use template meta programming. Something that we do in audio a lot is generating lookup tables at compile time. And since CppCast, we have const export containers, which makes that a lot easier. And we have const export math, which makes that a lot easier. So those are all really good things to like set up lookup tables or whatever other structures you need at compile time. So then at runtime, you have to do a lot less work. Another thing that, especially in gaming and audio, is very, very widespread is you don't use the actual mathematical operations that you get in the standard library. You either use faster implementations of those, or you use even faster approximations of those. So sometimes you don't need the exact result. It's okay if it's kind of not exact, but very fast. I guess a very, very famous example of this is from the 90s. Like that's the Quake 3 algorithm to compute inverse square root. This is something that you need to do a lot in gaming because you're doing 3D geometry. In audio, for example, we do the same for exponential and logarithm because we need to map between log space and linear space a lot. So there we have similar approximations for those functions. It kind of depends on the use case, but yeah, people come up with weird bit fiddling tricks to speed this up. And so this is going to be very, very, very fast. And it's going to give you the result within 0.1% precision, which for a lot of these cases is good enough. Of course, this is undefined behavior. Don't do that. Please do this instead, which is like what we added to the C++20 standard. It's going to compile down to the same thing, but it is defined behavior. I do have a talk from a few years ago, an hour only about basically this and how to do this correctly and what not to do. And it turns out that if you're doing this kind of stuff, very quickly you need to know about kind of the rules for like low-level programming in C++. So you're going to be starting to fiddle with bits. And so there's all these things that you need to know in order to not produce UB. And then having something that maybe works, but like if you go to a different compiler, everything just falls apart horribly, right? So if you're doing this kind of stuff, you got to know about object lifetime rules. You got to know about aliasing rules. You got to know about alignment rules, right? You got to know about like representations of objects and values, which are actually different things, like the bytes in memory. And if you cast something to something and then the bit pattern isn't a valid representation of a value of that type, you get UB and all of this stuff. We have actually on the committee done a lot of work recently to add tools to do this safely, but like to get the same performance while not introducing UB. CppCast is a particular example. I think that was JF's paper, who just, I think, left the room a few minutes ago. But thank you, JF, for this paper, which is a non-UB way of doing this. I want to look at the bytes of an int and pretend that they're a float. You can do this safely now. We also got implicit lifetime types, which is Richard Smith's paper, which is exactly in this space as well. You have some, sequence of bytes, and you want to pretend that it's an object of type widget and just cast it to a pointer of that, and that's UB. But since C++20, in some cases, it's actually not UB because we say that you get kind of the lifetime of that object starts at that moment. It's going to be implicitly created. And then since C++23, this is a paper that I was involved in, we actually have an explicit method of doing this as well, of like saying, okay, here's some bytes. I want this to be an object of this type without actually calling the constructor, because I know that those bytes are representing a valid value of that type, right? So you don't have to call the constructor. No runtime overhead, but also no UB. So yes, fast approximations, you really need to know these low-level things, which is what the other talk is about. Powers of 2 for sizes, that's something where I've seen, if you just use a power of 2 for a size, you get a 10x speed up in some cases, right? Because the compiler can change your divisions or modulo operations with just bit shifts. Lookup tables can a lot of the time be a lot faster than actually computing something that we heavily use in audio. And there's many, many other techniques. There's a whole world of talks about this stuff out there, right? But it turns out all of that is also not enough, because you also need to know your optimizer. Like if you have an optimizing compiler, they behave differently. They have different ways they do things. And you're going to run into surprises if you look at what your optimizer actually did. And this is I love Jason Turner's C++ Weekly. This is an episode that I watched literally a couple of days ago. And it was so interesting. Basically, he was benchmarking std pair versus a naive implementation where he just has like an template aggregate with like 2 members in it. And it turns out, well, they ought to be the same performance, right? Because std pair has a constructor that should inline and everything should evaporate. But for some reason, the compiler just wasn't doing that, even though it was in a header, it was all there. But the compiler just somehow didn't inline that. And so then he put like force inline attribute on the constructor, and then all of a sudden like you get like a 5x performance difference. So I guess the takeaway is not to sprinkle force inline over everything, but I guess the takeaway is to use these like very simple kind of aggregates and things like that over things that are, have 50 constructors, because, depending on your optimizer, like that might not actually evaporate away even if it should. And another thing is UB. And so we've talked about UB in the context of safety, right? Like we have all of this UB in the language, and it's bad, right? We can introduce UB by circumventing the type system, by having out-of-bounds access, by looking at memory and pretending there was an object where there isn't one, uninitialized variables, data races, integer overflow, all of the stuff, right? Like there are these delicious examples on the internet where you have like an infinite loop somewhere, and that leads to like the whole like program being optimized away, or like really surprising things. But actually, and I'm going to be kind of maybe the villain in this whole safety discussion a little bit, but undefined behavior can also be your friend, because if you do get it right, what the compiler does, right, if you have undefined behavior, is it just assumes that it cannot happen and then optimizes based on that assumption, right? But if you get it right, then you get all of these sweet optimizations, and this is what you want. And there is another talk by Further, I'm going to be mentioning your name quite a few times today, from this conference last year, talking about undefined behavior from a performance standpoint. I think it's a very, very interesting talk where you get like a little bit of a feeling for this, And in C++23, we took it one notch further. You can actually ride the dragon of undefined behavior kind of in an even more direct way. So we have attribute assume in the language now. So we had std assume aligned already in C++20. Both of these are papers that I wrote, and with attribute assume, it took 3 years to get it through the committee. We had quite a few heated discussions about this, but it's now in C++23. So it's that paper. So I'm not going to talk about assume aligned. It's like a very particular use case where that's something that you can't express with attribute assume. So we did that first. That was easier. And then we did the general one. And so this paper, basically what it does, and this is a toy example. Let's say we have a function where you divide an integer by 32. Okay, very boring toy example. And so this is, for example, what Clang produces with O3. Well, it kind of has to assume that it can be negative or positive, and like the instructions are going to do the right thing for every possible int that you can pass in. But now you can explicitly inject this assumption saying, well, I know that the number is not going to be negative ever, right? And so because it's an invariant in my code, and I know there's like somewhere in the code, some property of my code guarantees that this can never happen, but for some reason the optimizer doesn't see that because it's in a different translation unit, because it's, I don't know, you read something from a different, it's coming from a different programming language or whatever. Like the compiler cannot deduce that this is an invariant, but you know that it is, and so you can inject it directly. And then the compiler can say, well, I'm going to optimize based on this. So the way this attribute works is that the condition there is not going to be evaluated, right? But the compiler is going to say, it's going to assume that this condition is always true without evaluating it, and it's going to then optimize based on that assumption. So it's like, again, this duality of UB versus optimization, but you can now very purposefully inject it into your code. And so then the compiler is going to optimize based on the assumption that x greater equals 0 is always true, and then it can throw out all the instructions that deal with negative numbers and just turn that into a bit shift. Okay? And so this is obviously a toy example, but here's a more real example. So something that you might do in audio is you have a limiter, you have an array of floats. That's like an audio signal. A digital audio signal is basically just an array of floats. And you say, okay, I'm going to take this array of floats, I'm going to traverse through it and clamp all of the numbers in there to values between -1 and 1. Okay. And so that's gonna be probably in a very hot loop with real-time constraints. But then maybe you know something about this buffer because it maybe comes from an audio file format that you just read, and you just know how this format works, and you know that it has certain properties. And then you can inject these properties. and tell the compiler about them. You can say, well, I know that the buffer is never going to be empty, and I know that the size of the buffer is always going to be a multiple of 32. Let the compiler optimize the loop a lot better. And then you can also say, well, I know that none of the numbers in there are going to be none or infinite or any of this like special stuff. And then the compiler can actually go into header, wherever the clamp is. I think it's header algorithm, and actually optimize that too. And at least 2 of the 3 major compilers actually do that. And then you get much better code gen, okay, for this. And so you can see there's a lot more examples in the assumption paper, P1774. There's a lot more examples for this. So you get much better code gen. Obviously, if you then pass in something that violates these constraints, they're not checked. So everything's just going to crash and burn, and you're going to be in UB land. There's a comment there.
Yeah, maybe it's 0 for the previous slide.
Yes.
So I think it would be nicer, like the previous slide with the int.
Yes.
Yeah. I think it would be nicer to encode such assumptions not inside the function, but in the function parameter type, to pass not an int, but something like non-negative int.
Yes. Like the comment was, why don't you just pass an unsigned, basically?
No, not an unsigned, no.
No.
Like
a strong type.
Yeah, positive int, which includes this constraint.
Yes,
like,
I mean,
you assume somewhere inside.
Yeah, okay, so you can do that. You can have strong types where like the optimizer can deduce some of these assumptions by just looking at the type. That's what you mean, right?
Yes.
So yes, that's a great technique. Like this is a toy example, right? So sometimes it doesn't work. Like in this example, these properties come from, for example, some kind of binary file format that you just read. And so the optimizer just doesn't know about that.
But again, I can include it in the function signature. Like
yes, you can, but then maybe your audio API just deals with float pointers. And that's just the way it works. You cannot change that, right?
Yeah, so it's just, I think maybe it's just saying that we want these assumptions, those are preconditions basically, to somehow appear in a header file or in the function like declaration, not only its definition.
Yes, so I mean, then we are into this whole discussion about contracts, and let's not go there now. This is like a whole other talk. Yes, you can do this, and yes, we're working on getting contracts into the language. But yes, that's a whole other discussion. So I'm probably going to do a talk about this here next year. Yes.
No, I was just going to say he's probably talking about contracts rather than.
Yes. Question here?
Yeah, so I suppose if you, maybe in one case you know that, in another case you don't know that, so can you put that assume before you call the function and then the function is aligned, then for that particular call it uses the assumption, but in another case where you don't have the assumption, you just call the function.
Yes. The comment
so it aligns the
can you
the
not
assumption.
Just put the assumptions outside of the function? Then, yes, of course you can do that. You can do a lot of stuff. I'm talking about like how the language feature works that we introduced. But like the way you can use it is in many different ways, including this. Okay, I have lots of slides. If it is going to be a massive discussion about assume, we can do this during the break. But if your questions are short, we can take them now. No? Okay, let's have the proper discussion about assume during the break because it's a fascinating topic, but I don't want to, I have a lot more slides and 30 minutes left, so it is a big topic. I would say this is really an expert feature in the sense that it's so easy to shoot yourself in the foot with this, right? If you get this wrong, you're instantly UB. So I think this is something that you really should only be using if it gives you measurable performance improvement and if you're in this like really critical code where like every nanosecond matters, right? I think this is the only time you should be using this feature because it's really unsafe, right? And if you talk about safety and all of that stuff, you're basically injecting UB into a program. But there are cases where this feature gives you the kind of speed up that you need, and there seems to be, for some cases, no other way to tell the optimizer to do certain things, right? So it can be a lifesaver in certain very narrow performance critical situations. And so if you do this kind of stuff, I have this comparison in the paper where you get a lot better code gen, like a lot of instructions it's gonna be like on one compiler, I think it was a third of the instructions. But of course, as we already said, number of instructions doesn't equal runs faster, right? So people have looked at the performance of this. And there were several, especially when we were debating whether or not to standardize this and all of the stuff, there were people who brought up, Herb wrote a paper about assumptions a few years ago where he said, well, we just turned all our assertions into assumptions in some Microsoft code base. And then actually everything ran slower, right? Plus also we got crashes and stuff, but everything ran slower. There was another paper by, I forget the name now. Oh, I think it was Parsa Amini. I think 2 years ago, where he did the same for Bloomberg's code base, I think, and then he found that there was no statistical difference between assumptions and assertions. They don't give you speed up or slow down. And there's this more recent paper by John Lakos and others where they did find that assumptions give you a measurable speed up, right? And so it really, really depends on the use case. Sometimes it can be slower with all of the stuff. Sometimes it can be slower, sometimes it can be faster, sometimes it doesn't matter at all. Most of the time it doesn't matter at all. So you really, really need to measure. And so we have now a language that assume aligned, which where you can assume that a pointer is aligned, which is something you can't really express with just assume. There isn't an expression that tells you this address is aligned with this because of the way alignment is defined in the standard. You can't really write that as an expression, so we need that as a separate feature. Then we have the general assume in CSS23, and there's one more which we don't have, which I really, really think we need, which is talking about a pointer not aliasing another pointer. And so in this case, we are passing in two pointers, but because they're of the same type, the compiler has to assume that they may alias each other. So the way it compiles these three instructions is that it cannot assume that if you increment B, you didn't increment A. And so it has to execute all of these three increments, right? But if you, in C, there's a magic keyword called restrict, where you can say, well, A is actually not aliasing B. And then the compiler can say, okay, well, that means B, if you increment B, I'm not changing A. And so it can reorder these and like squash the two increments of A into one instruction. And then it's faster. And this is one of the reasons why people say Fortran is faster than C++, because Fortran has no aliasing. So Fortran always compiles down to like the bottom version, right? And so restrict in itself wasn't, like Bjarne didn't want to have it in C++ because it messes with the type system. It has lots of properties that we don't want. But I think what you want is you want an attribute, an ignorable attribute that does this, right? So I am going to propose this for CSS26, and I'm going to see if it's going to fly. But I think there are cases where you get measurable performance improvement if you have something like this. And so, I'm gonna write a paper introducing a no alias attribute, unless somebody convinces me that it's a terrible idea. And this is actually something that in the original paper from 2008, while the committee was working on C++11, way before I joined the committee, they already said, this is something that would be a good attribute. And most of those things on the list in the original 2008 paper, they actually became attributes, but not this one. So I'm gonna propose that. And then there's two more, which are also kind of in the space, which are now being added or have been added to the C standard. C23 is going to have these two attributes. And we don't have them in C++ yet, but I think we should, and I'm going to work with the authors of this paper to hopefully get those into C++. So this is a paper by Etienne Alepin and Jens Gusted. And so that's a C paper, right? So they proposed these attributes for C. And if you know a GCC, basically reproducible is pretty much the same as GNU pure, and unsequenced is pretty much the same as GNU const. There are slight differences. The standard versions, there's like a few more places where you can put them, like slightly less strict, like where you can put them, but like the semantics are the same. And so what do they do? So this is from the paper that they wrote from the C paper. So you can reason about these properties of functions. You can say a function is stateless if it doesn't define mutable static or thread local objects. It's effectless if it doesn't have observable side effects. It's idempotent if you call it multiple times, you get always the same result. And it's independent if it doesn't depend on any other state outside, which basically means it doesn't matter when you call it, and it's going to give you the same result. And you can combine those 4 properties and say, well, a reproducible function is effectless and idempotent, and an unsequenced function has all of these 4 properties. And then basically what they said is, let's have attributes where you can tell the compiler that my function has these properties, and it's not going to check that. It's just what they assume. It's not going to check that. It's going to assume that those properties hold, optimize based on that assumption. If you get it right, you get a performance improvement. If you get it wrong, you get UB. So here's an example. And this is, by the way, I think it's going to be a lot more common than assume. It's going to be pretty much, I think, every math function you can put this on almost. Let's look at cosine, for example. We have cosine, which is an expensive function call, and then we have some formulae which calls it 4 times. And then the compiler, if it can't see the definition of cosine for some reason, or if it's like too complex, it can't optimize it, it's going to generate these 4 function calls, right? Especially if they're in a different translation unit, it can't optimize that. So it's going to generate 4 function calls. If you put unsequenced on it, well, it can say, well, here I call a function 2 times with the same argument. I know it's unsequenced. I can assume that both calls are going to give me the same result, and I can optimize away one of those calls and reuse the result. And that might be a massive performance improvement. And by putting this attribute on the function, you can tell the compiler to perform this optimization. And they got that in C23, and I really, really think we need that in C++ as well. So I'm going to ask the authors or work with the authors to get that hopefully in CSS26. There is a comment here?
Yeah, I think in many cases, the compiler that sees the code for cosine can prove that such a function is unsequenced or pure or whatever. And in module land, where the declarations are not header files that we write, but BMIs or binary module representations that the compiler generates, it would be very, very nice if the binary representation for module will automatically just write down that the function is pure.
That's a great comment. So yes, if it's in a header file, the compiler ought to see this and do these optimizations. Sometimes it doesn't. It would be great if modules can solve this, but I don't think they do, but I'm not a modules expert. So, Ben?
This example uses the OR operation, and that's defined sequencing. If it used another operator which doesn't have the defined sequencing, could the compiler already do this? Because otherwise it would be UB.
If you don't have an operator that defines sequencing like the OR operator, couldn't the compiler already do this? Well, the compiler can't assume that there's no side effects.
Yeah, cool.
Well, the compiler can't assume that the compiler doesn't know the difference between cosine and rand.
Yeah, basically. Yes.
Right, but the compiler doesn't have any constraints over which order it calls them in. And if
but it has to call it twice.
It has to call it twice.
It has to call it twice.
Cosine with rand.
Maybe there is a printf in there, and it would be.
Okay.
It has to do that twice, right? Because otherwise, it's not. You violate the as-if rule. So the compiler cannot violate the as-if rule unless you tell it that it's fine because it's going to be the same anyway.
Yeah.
The same
the order would get defined. You're right. The order of evaluating the it would be a binary function, and the order of evaluating the arguments would be undefined.
All right. So
cosine might be a magic function for the compiler. We might know more. Might be.
But this is again a feature for the general case. In general, you want these optimizations to happen. For concrete cases, maybe there's other magic that might get you there.
I guess this works if the compiler can be sure that angle 1 doesn't change between the 2 poles.
Yes, like I'm assuming this is a const, like local variable. Yes.
Well, it's passed by values.
It's passed by
So that's a pass by value. That the compiler knows.
Yeah, but what are you passing by value? It could be a reference.
It doesn't matter. Threads are not involved, and while you're evaluating this, you're not doing anything else. else.
Okay, let's move on. Okay, I have 15 minutes left and a lot of slides, so let's see how this goes. So something that I'm gonna whiz through because I think a lot of people are familiar with this matter is this, right? So we talked about the optimizer, the language, efficient code, but you cannot really write efficient code if you don't know the hardware architecture and the properties of the hardware architecture, which involves, the CPU, instruction set, pipeline, SIMD, cache hierarchy, prefetcher, branch predictor, all of that stuff, right? You need to if you want to do low latency stuff and if you want to do efficient code, you need to keep all of these things in mind, right? So it's actually tricky to get good information on this. Like Agner Fogg obviously has these legendary optimization manuals about the x86 instruction set and what it means for optimizations, but I don't know anything like this for ARM. If somebody does, please let me know.
There's so many different variations of ARM.
Yeah. So we obviously have the CPU pipeline. This is a picture from Wikipedia where there's 4 stages in the pipeline, and there is always this problem that you kind of execute instructions kind of simultaneously, and if the result of one instruction is needed to execute the next one, then you have a problem because you have a pipeline stall, right? And so this is, I think, a very outdated picture. A more modern one is here, where there's actually more like 20-something stages, and a pipeline stall would be 10 or 15 cycles or something like this. And we have different types of hazards here, right? So we have branch hazards, where we might branch on something and we don't know which the next instruction is going to be, and so then we would need to rely on the branch predictor to give us this performance. So here's one of my favorite examples. You have a vector of floats, and then you put a bunch of numbers in there, which might be negative or positive. And then let's benchmark how long it takes to count how many positive numbers we have. Okay, I'm just going to benchmark just this bit here. And then I'm going to sort the vector. I'm going to benchmark it again. Okay, it's going to be the same amount of positive numbers in there. So it's going to be the same instructions, the exact same instructions that's going to be performed here. But it's going to be, depending on your compiler and depending on your CPU, it might be many, many times slower, because either it's random whether the condition holds or not, and then the branch predictor can't predict it, or it's like all negative and then all positive, and then it's very easy for the branch predictor to predict it, right? And then you're not going to suffer from this penalty of the branch, right? So there is this whole topic of how do you program in a way that avoids branches, which is a whole topic in itself, a whole talk in itself, which I don't have to give because Fodor has already given it a couple of years ago. Another great talk. Just a couple examples from that talk. It turns out that sometimes it's actually faster to evaluate kind of both arguments instead of just one, because it saves you a branch, right? And it can be that, for example, whether x is true is more or less random, so the branch predictor can't really reason about it, and whether or not y is random, y is true is also random, so you get 2 branch mispredicts. But it really depends on your use case. Sometimes the combination of them might be more easily predictable, and then even you're doing more work, right? So you're not short-circuiting. You're doing more work, but it's actually faster because the branch predictor can predict it better. And here's another example also from Fodor's talk, where you have like a conditional, and you can transform that into a branchless version, where you put like both expressions into a array and you evaluate both of them, right? So it's more work. And then but you kind of index into that, and depending on the properties of your system, it might be very much slower or faster or no difference. You have to measure, right? One thing that I want to mention, another set of attributes. So it seems like you want to hint to the branch predictor in certain cases that this branch is more likely to be taken, right? So for example, in finance, you want to figure out if you want to place the order or not. And if you do want to place the order, it needs to be really, really fast. So you want the branch predictor to take that branch. So it seems like you could put this attribute there because that's what it's for, right? Turns out, no. This is actually not at all what this does. Likely and likely does not affect the branch predictor at all, because there are actually no instructions that the compiler could emit that would give hints to the branch predictor. On some older CPUs, such instructions exist. On modern CPUs, to my knowledge, such instructions do not exist. And therefore, no attribute in the world could actually give any hints to the branch predictor. What it does affect is it affects code layout. And that might or might not, have an interaction with the instruction cache. But that highly depends on what you're doing. And actually, in some cases, again, these attributes can actually pessimize your code instead of optimizing it. And there's a blog post by Aaron Bauman about this, and there's like a 1-hour talk by Amir and Tomer about likely and unlikely and how that affects performance. And it's a very surprising deep dive talk into this topic, which I highly recommend. Another thing that you can have is data hazards, right? So if the result of, you don't have a branch, but the result of an instruction is needed for the next instruction, and then again, you have this problem with the pipeline. Here's an example where you have some kind of naive implementation of A to UI, like you're taking a string which encodes a number and you parse it and you return the actual number, right? And so this seems like it's efficient, but the problem here is that you have this hot loop, and like the result of one calculation is immediately needed for the next one. And then you have a problem because you have a branch hazard, right? And so there was a talk actually a while ago by Andrei Alexandrescu about pretty much this example and how to make this more efficient, which is again very interesting and surprising. But yeah, that's a data hazard that can have a massive impact on performance. And then the most weird one is a hardware hazard, which is something that I haven't known for a long time. I didn't know about these things. It turns out that sometimes there's also just a property of the CPU that results in a pipeline stall. Like for example, you have a limited amount of adders and shifters on your silicon, right? And so if you're doing too many of these things at the same time, you might not be able to do something in one instruction. You also have a limited amount of load and store units. So I think on the latest Intel CPUs, you can do 3 loads and 2 stores per cycle. If you do something else, you might have a slowdown because of the way the CPU is constructed. So one trick that you can do sometimes, you can replace a load by a shift. You can increase the bandwidth of every load by using SIMD. This is something we're going to look into as well. And another type of hardware hazard is just a hardware bug. So this is something I found on Stack Overflow like just yesterday, and I found that really fascinating. So somebody is computing the pop count of a large array, basically counting how many bits are set in a large array. And so they figured out, okay, they have to manually unroll the loop because the optimizer doesn't do that. And then they actually even introduced manual SIMD instructions there because that speeds it up and everything's great. And then they figured out if they change the loop variable from unsigned to size t, their code is twice as slow. Twice as slow, right? And it turns out it's really fascinating that this is like a hardware bug in the particular type of CPU that they were using, where because of the way the silicon is designed, like this pop count instruction that they were using has a false dependency on a register that was used for the other thing. So even though there is no logical connection, like the CPU is just constructed in such a way that if you execute this instruction, you're going to have to wait on some other instruction to finish, and so that gives you this slowdown. So yeah, this is the kind of stuff that you run into if you do ultra low latency, and I think it's really really fascinating. So one more kind of hardware-specific aspect that I want to go into very quickly is SIMD, single instruction multiple data. We had a talk by Jeff Garland yesterday about SIMD. Yes, depending on your CPU, you have these registers, right? Like width of 128 bytes or 256 or however long, right? Bits, sorry. And so you can execute multiple multiplications or additions, etc., in one instruction. And so there's different ways to interact with this, right? You can let the compiler auto-vectorize stuff, which works sometimes, and you get this 4x, 8x speed up, not doing anything. You can explicitly vectorize your stuff using SIMD libraries, and this is what Jeff Garland was talking about yesterday, there's a bunch of libraries for this, and one of them is actually on track to be in C++26, which is very exciting. And then you can also write intrinsics by hand or even write assembly by hand. And there's another technique that I learned from some trading people where you can also do SWOR, which is like SIMD within a register. So you don't actually use SIMD, but you just use a regular 64-bit register, but you put two 32-bit numbers in there and you do one operation on both of them. And there's all kinds of tricks like that. So auto-vectorization, right? A lot of the time it works if you do something naive like this. You just have a loop, you multiply an array with a number. A lot of the time the compiler is going to generate this code for you, where the purple bits are like the stuff in the loop. Often you get this like prologue for like the bits that are maybe not aligned with the SIMD register size, and then you get like the main loop, and then you get like an epilogue. And you get these SIMD instructions, which gives you a big speed up. Turns out auto-vectorization is quite brittle. It's highly dependent on the compiler, whether it does it. It typically only works with like contiguous arrays of numbers, not with structs. Classes. So if you want to do SIMD with classes, you kind of have to like turn it inside out and have structs of arrays instead of arrays of structs. In order for auto-vectorization to work, you have to traverse the data linearly. You have to use a for loop. Typically, like the compiler needs to reason about how many iterations you're going to have. You can't have any, if you have any kind of data-dependent break or goto or something like this, typically auto-vectorization is going to fall apart. If you have a conditional inside the loop, typically auto-vectorization is not going to work. If you have data dependencies between different elements of the same array, typically you don't get auto-vectorization. And if you have aliasing between the arrays, you also typically don't get it. And you might not get it even if you do all of this, right? Depends on the compiler. So here's an example. So we have these three arrays, and we're doing something with them. Doesn't really matter what we do, but then we have this dependency here where inside the loop we're referencing bi and then also bi plus 1. And so that means the compiler cannot auto-vectorize this, but you can basically do the exact same work by just shifting your loop by like half an iteration and reformulating it like this. If you stare at this long enough, you're going to realize that it's doing exactly the same thing as the code on the left, but you eliminated this thing where you reference different elements of the same array in the same loop, and then you get auto-vectorization. So the left code just has normal instructions, the right code has the kind of SIMD instructions. So depending on what SIMD you're using, it can be 4 times, 8 times faster, right? Just by doing this little transformation. But a lot of the time, like you can't do that, or the optimizer just still can't figure it out, and that's when you need explicit vectorization libraries. And this is what Jeff Garland was talking about. An example is the Mandelbrot set. If you want to compute that, this is example code that does that. You have like a termination in the loop, so it's not going to auto-vectorize it. Another example, which is from audio, you're doing convolution. So you basically have a long array, and then you have a kernel, and you convolve the two. So basically you're multiplying the source with the kernel, then you shift it by 1, you multiply the source with the kernel, you shift it by 1, you multiply the source with the kernel, you do this all the way down. And so you might get SIMD instructions for some of this stuff. So this is kind of a naive implementation of this. But it's not the most optimal way to do this. The most optimal way to do this, because you want to be aligned with the SIMD register size, is to have, if for example, your SIMD width is 4, you want to have 4 versions of the kernel like shifted by 1, 0, 1, 2, and 3, so that all of them are aligned with the SIMD register size. And then you get faster code. And this is not a transformation that any compiler would ever do for you, right? So that's when you have to go in manually, redesign your algorithm for SIMD, and put the SIMD instructions in there by hand by using libraries that do that, right? And then you get a massive speeder. So that's good. Sorry, what is that? Okay, yeah. And so another thing with SIMD is that if you know, and again, it depends what industry you're in and what you're doing, right? If you know your exact CPU they're going to be running on, you can just use the exact like compiler flags to like get the right SIMD instructions for that exact CPU, right? If you do something like games or audio where you're going to be running on consumer hardware and you don't know what level of SIMD they have, it's more difficult, right? You can compile for like the most common denominator on Intel and on ARM, It's not going to give you the best speed up. What you can do is you can compile different versions of your kind of mathematical, like numerical kernel for the different SIMD architectures. You can have a version for SSE, a version for AVX, a version for AVX 512. And then at runtime, you cannot do this at compile time. It depends on what machine this is running on, right? And at runtime, you can do one check when you start up the program. Okay, ask the operating system what instructions do you support, and then dynamically dispatch to one version or the other. And GCC and Clang actually let you do that. Like they have a feature for this. MSVC unfortunately doesn't, and then you have to do it by hand. But with GCC and Clang, we have this thing called function multi-versioning, which is really cool. So you can, it's a little bit like overloading on hardware properties, right? So you can have multiple versions of the same function. You can put this attribute target in there and like say, okay, I want to compile this version for this architecture. And then it's going to do all the dynamic dispatch basically for you automatically. Unfortunately, you can't do this if you want to ship on Windows, so then you have to do it by hand. All right, I think we're at time. I'm not quite done with this part yet, so we can either overrun by a few minutes now, or we can go for a break and continue from here after the break. Is that better?
I think go to break.
Okay, let's go to break and continue from here.
Get up and move around.
We're going to do exciting real-time stuff in the second part.